Welcome to The Explainer. Today, we're diving into the surprisingly dramatic world of mathematical logic to unpack a really fundamental conflict between what's elegant and what's actually efficient. So let's just start with a core question. What do you think makes a proof perfect? Is it the one that's the most pure, the most fundamental, built from the absolute ground up? Or is it the one that's the most direct and just gets you to the answer as fast as possible? Well, as we're about to see, you can't always have both. All right, here's how we're going to break this down. First, we'll talk about what this so-called perfect proof is. Then, we'll get into the huge problem it creates, why it happens, and finally, the really clever ways people are trying to fix it. So what is this perfect proof we keep talking about? Well, in the world of logic, it's all about building an argument with just absolute, undeniable clarity. No shortcuts. It's called a cut-free proof. And here's the easiest way to think about it. Imagine you need to use Pythagoras' theorem for something. Instead of just writing down a squared plus b squared equals c squared, a cut-free proof would make you prove the entire theorem from scratch every single time you use it. Yeah, it's perfectly pure, totally analytic, but man, is it a lot of extra work. And that right there, that's the core of the paradox. This theoretically beautiful, pure method of proving things has this massive practical downside. It seems like purity and simplicity just can't get along. Okay, so let's talk about the cost of this purity, because this is where a small problem blows up into a huge one. Turns out, when you insist on this level of perfection, you can end up with total computational chaos. So this really lays out the two sides of the coin. On one side, you've got the pure, analytic, but often crazy, inefficient cut-free proofs. And on the other, you have the proofs we all normally use, the ones with cuts, which are basically shortcuts or lemmas. They're quick, they're practical, because they lean on things we already know are true. It's a choice, really. Purity or speed. In fact, this problem is so bad, so completely counterintuitive to logicians who absolutely prize elegance, that experts gave it this really dramatic name, the computational scandal. So what makes it a scandal? Well, it means these supposedly pure systems can't even handle basic logical tasks efficiently. Things like verifying a simple truth table. To put it in computer science terms, they can't polynomially simulate them. That means a simple problem can cause the proof's complexity to just explode. It's kind of like building a high-performance race car that can't want to race against a tricycle. It just doesn't make sense. And what this scandal leads to is something that logicians call proof size blowup. And it is exactly what it sounds like. And if you want to see what this looks like, just check this out. A proof that's nice and short when you use a lemma, a shortcut, can become exponentially, almost impossibly larger when you're forced to do it the pure cut-free way. And we're not just talking a little bigger. The truly wild part is that the increase in size can be so extreme that there's no standard mathematical function that can even describe it. It's an explosion in size that's just hard to wrap your head around. So this begs a huge question, right? If these proofs are so pure, so perfectly built from first principles, why are they so bloated? Where is all this extra stuff coming from? And the answer, well, it's pretty surprising. Researchers started digging into these monster proofs, and what they found wasn't some hidden flaw or impurity. The problem was just massive, massive redundancy. What they discovered was kind of mind-blowing. Any proof that had blown up to that crazy exponential size was, by its very nature, just repeating itself. It had to contain at least one smaller piece of the argument that was being repeated over and over and over again, sometimes an exponential number of times. This was the smoking gun. It meant that if you could just find that repetition and get rid of it, you could shrink the proof right back down. Okay, so this brings us to the really cool part, the clever ways researchers are now trying to get the best of both worlds, to keep that analytical purity while taming these gigantic proofs. One really elegant solution is something called an analytic cut. You can think of it like a carefully pre-approved shortcut. It's a way to bring back a simple, direct lemma that doesn't mess with the core principle of building from the ground up. So you get that efficiency boost you need without sacrificing all the logical rigor. Another way is to build totally new algorithms. There's one called unthreading, and it does exactly that. It takes a complex, tangled-up proof and just systematically untangles it, simplifying it step by step, until it's as small and clean as it can possibly be. You're guaranteed to get something that is both pure and as short as possible. But maybe the most mind-bending idea of all involves temporarily breaking the rules. Seriously, researchers are playing with the idea of allowing logical steps that, if you look at them in isolation, are technically wrong. They're unsound. But as long as the proof as a whole still works out correctly, these tiny controlled moments of wrongness can help find a much, much shorter path to the right answer. And by doing this, by breaking the rules just a tiny bit in the right places, researchers can get what's called a non-elementary speedup. And as you can see here, this isn't just a small fix. This is a way to shrink proofs by an almost unimaginable amount, way beyond what any traditional method could ever do. So what's the big takeaway here? Well, it's that the perfect proof isn't always the most useful one. The search for theoretical purity accidentally led to a computational disaster. But it turns out that disaster was caused by hidden repetition. And now, all these amazing new tools are being designed to bridge that gap, finding incredible ways to make proofs both elegant and efficient. And that kind of leaves us with a final, pretty provocative thought. It seems that even in the super rigid world of mathematics, sometimes the fastest path to the truth might require a little creative rule bending along the way.